Welcome to the first lesson ever of chemistry. Um, and the name is Matter and Energy. What is chemistry? So I assume that you've learned biology before. So many of the stuff and I assume that you've learned basic science before. So many of the stuff that I'm repeating, uh, and many of the stuff that I'm going to say, um, many of the stuff that you've already learned that is present in this textbook right here, unknown author, it's Introductory Chemistry by the Sailor Academy, published by the Sailor Academy. So that's the textbook I'm going to be using, but many of the things that are in this textbook I'm going to skip because I assume that you already know biology and from the ninth grade. So this is supposed to be a 10th grade course, but I assume that you already know biology. So today we will be doing introductory chemistry, and I will be teaching you what is chemistry, basically. So we'll be learning what chemistry is once and for all. So chemistry is the study of matter and interactions of matter and energy and matter. That's chemistry. It's a study of the interactions between matter and energy and matter. Right? That's it. There's nothing tough about it, right? But just with these two specific areas of chemistry, with these two specific areas, you can get a lot out of this. So we'll be going through a lot of energy, we'll be going through a lot of matter, we'll be going through the smallest matter, we'll be seeing what happens inside of that small matter. But chemistry is the study of matter interacting with energy and other matter. What is matter? Matter is anything that has mass and occupies volume, right? I forgot a D right here. There you go. Has mass and occupies a volume. So, which of these is matter? Is a book matter? Yes, it is, because it has mass and it occupies volume. Is love matter? It's a noun, but it's not matter because it's a feeling, and that feeling doesn't have mass. That feeling does not occupy any volume, right? So not matter. Light, does that matter? It's actually not, because light has zero mass. And it actually I don't think you can actually measure light based on volume, because light disintegrates the farther you are from that light. So light basically has no volume and it has no mass. It's actually not matter, it's actually energy, right? Water is matter because water has a mass and occupies a volume. Plasma is matter because plasma has a mass and occupies volume. Although it's really hot, it still occupies volume and has mass. And ice is a matter because it occupies a volume and it has mass. And this is my unforsakenly bad drawing of ice, right? I'm going to try to draw some of these interactions, and they're going to be pretty bad, but just bear with me because I'm actually trying. So, next slide, we have our physical changes and our chemical changes. What's our physical property, physical change, chemical property, chemical change, right? So physical reactions are reactions that change the matter, a state of matter as it exists, meaning there's no change in the composition of atoms, just its shape and way that it behaves. So, for example, if I take if I take a person and then I run a car over that person, the person's dead, clearly, and there might be some chemical reactions that are happening in his body to render him dead, but the reaction of car running through him it's just a physical reaction because the force that it takes for the car to hit him makes him die. So car running through a person is a physical reaction because it changes the state of matter as it exists. It makes it smaller. It doesn't actually change the state of matter, but it makes it into smaller bits. But there's no change in composition of atoms. There's still a bunch of atoms, and its shape is changed because it's broken into small bits. But chemical reactions are reactions that do change the composition of matter into a different kind of matter. For example, two hydrogen gas, and oxygen gas will make water, or dihydrogen oxide, dihydrogen monoxide. So, which one's a chemical and which one's a physical? Number one, water in the air turns into snow. Is that a physical or chemical reaction? It's a physical reaction because water turns into snow. It changes shape, changes the way it behaves, but it doesn't change. It changes the state of matter, but it doesn't change the composition of atoms. It's still H2O. It's still dihydrogen oxide. So it doesn't actually change anything except its shape and its state of matter. A person's hair is cut. Same thing. The shape changes, but the matter doesn't change. It's still hair. It's still keratin. So that is physical, and that's physical. Bread dough becomes fresh bread in an oven. Yes, that is a chemical change because even though the bread is heating up, because the bread is heating up, it's turning into this dough texture, and the yeast from the dough makes bubbles inside the bread. That's why there's so many bubbles in the bread. Carbon bubbles inside the bread, and then those bubbles rise out of the bread to make the bread look big, right? And that's why bread is big, and that's why other food is big. So it's a chemical reaction because there wasn't carbon in the beginning, but now there's carbon, right? That means that there's definitely a change in atoms. Fire is raging in a fireplace. Yes, that is a chemical reaction, and the reason why it's a chemical reaction is because in order to burn, first of all, fire is kind of it's not really a thing. It's not really a physical, like, elemental thing. It's just because something is so hot, it gives fire away, right? So the fire comes as a form of energy, right? But then let's say the wood or the coal turns into, like, changes color, which is obviously a change in composition of matter. It changes color, and it becomes like gray, whereas wood turns into ash. And I'm pretty sure wood doesn't actually turn into wood changes color. Wood isn't actually made out of ash. So if you combine all of the ash together, you probably can't make wood, because you don't have the energy to, right? Next, water is warmed to make a cup of coffee. This is a physical reaction because to make a cup of coffee isn't really part of the prompt, right? If you mix water into the cup of coffee, that's a chemical reaction, right? But water is warmed. That's just a physical reaction because it changes the state of matter, but it doesn't actually change the composition of atoms. So a sample of a same type of matter is collectively called as a substance. So if scientists are referring to two substances, they aren't actually saying, like, two single matter. They're referring collectively that as two substances, two things. One big substance, one small substance. That doesn't make sense. You have to refer to them individually as substances, right? And chemistry recognizes two types of substances: elements and compounds, right? Elements are the single simplest type of substance, cannot be split without releasing an extreme amount of energy. It should be energy, not power. I'm using the wrong terminology. I am extremely sorry. Energy. So there are 118 elements in something called the periodic table. I'm pretty sure you've heard it before. Here's the periodic table. 80 of them are stable, and 38 of them are radioactive. Normally the ones that are later down are normally radioactive, but some of them sprinkled in are also radioactive. And I don't remember all 38 of the radioactive elements. I'm not crazy. So compounds are combinations of more than one different type of element. For example, water, dihydrogen oxide, or bleach, sodium. I think it's sodium hydroxide. But compounds have different chemical and physical properties than its constituent element. So, for example, say a citric acid. Actually, I don't even know the chemical. Acetic acid. So CH3COOH. That doesn't have any of the properties of carbon, which is malleable. Carbon's not malleable. It's a good conductor. Oxygen, which is needed for everyone to live. We need oxygen to live, but we don't need acetic acid. And hydrogen, which is a really light gas. And acetic acid isn't a gas; it's normally a liquid. So they normally have different properties. And there are over 50 million compounds that are known, and more are being discovered daily. Now, matter can also be present in mixtures, combinations of two or more substances, like these right here. These are mixtures, right? Mixtures because there's two different types of elements. This is two different types of elements. One of them's an element, one of them's a molecule. This one's called molecule. These are two different types of molecules, and this is a molecule and a compound, right? This might be water. Let's say hydrogen gas and water, right? And these mixtures can be separated into two types, homogeneous and heterogeneous. I don't know how to pronounce this. I'm pretty sure it's pronounced heterogeneous somewhere, or heterogeneous, but I'm going to say homogeneous and heterogeneous. Homogeneous mixtures are also known as solutions. So here, how do you differentiate between the two? This is a homogeneous mixture right here. So think of water and salt, right? When you put salt in water, you mix it, boom. Salt dissolves, boom. You get a homogeneous solution of salt water. Heterogeneous, think of pretzels. So pretzels, they don't actually have a uniform thickness of salt. They have little salt cubes. So heterogeneous means some places are more dense than others in that mixture. So there's more bite of salt in some places of the pretzel than other places. So that's what makes up a heterogeneous mixture. A homogeneous mixture is also known as a solution, because if you put salt and water, mix it, that becomes a solution. So which of these are homogeneous and which of these are heterogeneous? Soda water. Carbon dioxide dissolved in water. Well, carbon dioxide dissolved in water, dissolved means it's a solution, so solution is homogeneous. Soda water is homogeneous. A mixture of iron metal filings and sulfur powder. Both iron and sulfur are elements. Well, since it's not a solution, because we're mixing two solids, it's heterogeneous. It's not homogeneous. The human body is definitely heterogeneous. Which place has more fat, the brain or the feet? Obviously, the brain has more fat than the feet. So the human body is a heterogeneous solution. 2. An amalgam. A combination of some other metal. I don't even know how to pronounce that. Some other metals dissolved in a small amount of mercury. Since there's dissolved, it's a solution, and solutions are homogeneous. So amalgam is homogeneous, or amalgam. I don't know. I don't care. Right? Elements can be divided into 3 groups: metals, nonmetals, and metalloids. And I'm not going to say semi-metals because that is actually like a stupid name. But if you want to memorize it as semi-metals, you can say semi-metals or semi-metals, right? Metals. I'm gonna list you some of the properties of metals. That metals are malleable. That means they can be squashed and pounded easily without breaking or like separating. Solid at room temperature, except mercury. Most of them are solid at room temperature. Mercury is not. They're shiny. They conduct electricity. They conduct heat. They're ductile, so they can be shaped into wires, right? Like copper. Copper wire is really, really thin. Non-metals are brittle when it becomes a solid. Here, look at this. Look at this oxygen gas. It looks like I can just break it in half, right? They're not malleable. So it looks like one of those metals where you could just karate chop it and then it would split in half. They're not malleable at all. They can't be formed. They don't conduct heat and electricity well. This really does not look like it conducts heat and electricity well. And does not necessarily have to be solid at room temperature, right? Metalloids have some properties of both depending on the element. So non-metals. This is an oxygen gas. It's a non-metal. It basically has all these properties. Metal. These are actually shaped into thin wires. They're not thin, but these are shaped into wires. So there you go. That's a metal, right? They are malleable, so they could be melted and they could be shaped into even weirder shapes. But that's metal, titanium metal. So this metalloid is silicon. It's shiny and it looks like it conducts electricity. That's why it's used a lot in computers, but it doesn't have the other properties. For example, it might not actually be malleable, or it might not actually be able to drawn into thin. Actually, it can, but it might not actually be malleable. So, or maybe it's just a metal. I don't know, but there's properties that distinguish metalloids from metals, definitely. Here are a bunch of questions. I'm just going to answer all the questions with you. Identify each as matter or not matter. Is a book matter? Yes, it is. Alright, I'll give you 10 seconds to answer the rest of the questions, all of the questions, and then I'll answer all of it. Okay. Looks like our 10 seconds is over. So, 10 seconds. Hate. Hate is a feeling, not matter. Not matter. Light. Light is, I'd like to say it's matter, but it's a form of energy. It's not matter. Car. Matter. It has mass. It's really heavy. Friday. Matter. Which one's a physical? Which one's chemical change? Graphite, a form of elemental carbon, can be turned into diamond, another form of carbon, at very high temperatures and pressure. Now, this is it really, you might be really tempted to say it's a chemical change because it's a change of carbon. It's a change of the composition of atoms, but it doesn't actually change anything in the atom. And it's used high temperatures and pressures, which is a increase in energy, which normally contributes to a state like a liquid. And pressure is more like a physical thing than a chemical thing, so it's physical. House across the street has been painted a new color. Painted means touching, and touching in order to change a house is physical, not chemical. Elements sodium and chlorine get together to make a new substance called salt. That is a chemical change because it literally says it right there, change of elements. Identify each as a heterogeneous mixture or a homogeneous mixture. Salts mixed with peppers. That no one can ever make that a homogeneous mixture, so it's heterogeneous, right? Sugars dissolved in water. Dissolved. Homogeneous. Pasta is cooked in boiling water. Now you can really see the chunks you can really see the difference between pasta and water. So it's definitely heterogeneous. Okay, air. Is air a homogeneous or a heterogeneous mixture? It's actually a homogeneous mixture. Right? Is dirt a heterogeneous or homogeneous mixture? Heterogeneous. Television set? Definitely heterogeneous. In exercise 9 and 10, which of these are also solutions? air, and this is solution, and this is a solution. So all homogeneous mixtures are solutions. 17. Elemental carbon is black, dull-looking solid that conducts heat and electricity well. It's very brittle and cannot be made into thin sheets or long wires. Of these properties, how does carbon behave as a metal? How does it behave as a nonmetal? So it behaves as a metal because it conducts heat and electricity well. It behaves as a nonmetal because it's black, dull-looking, it's brittle, and it cannot be made into thin sheets or long wires. So these are the nonmetal properties. I'm going to color code them. These are the metal properties. These are the nonmetal, and these are the metal. True silicon is shiny and silvery, but does not conduct electricity or heat well. Of these properties, how does silicon behave as a metal? How does it behave as a nonmetal? Well, cannot conduct electricity and heat, so it's not a. So it's a nonmetal, and then shiny and silvery, so it's a metal, right? That's why it's a metalloid, because it doesn't conduct electricity or heat, but it's shiny or silvery. That's gonna be it for today's episode. We'll start with numbers on the next episode. And I really need to be pushing out my history lessons, but that's gonna be it for today. And see you later for the next lesson.